it all. The first plot, you have what happens when you add more layers to your network. And what you see, if you have all the other fixed parameters, you see as you increase more layers, your error go down. You were expecting this, I guess. But the calibration error kind of goes up until a certain point. So this means that shallow networks usually are more calibrated than deep networks. This is the key take that you should take from this picture. The second graph is about if you keep the same number of layers and the rest of the parameters, but change the width of the layer, how many neurons per layer. And what you see is that as you, well, in this case they changed the filters, but it's pretty much the same. As you add more neurons to a given layer, usually the error goes down. I suppose this is the test error, but I don't think they are specific about it. Oh well, let's suppose this is the test error, for argument's sake. The error usually goes down, and the calibration error goes up, which means that if you sum up these two pictures, as you have more trainable parameters to your network, it will probably be better in terms of accuracy, but its calibration quality will go down. The third picture, they were not able to explain why this happens, but what they measured is when you apply batch normalization, your error usually goes down and your calibration error goes up. So if you are using batch normalization and you are concerned with the calibration, maybe you can experiment with dropping the batch normalization to see if it helps in your case. Last experiment they made was changing the weight decay with all the rest of the parameters fixed. And what they realized is that as you increase the decay, usually the error goes up, because if you decay very fast, then well, your regularization, it will be very hard to learn because it has a very, very high regularization parameter. However, the calibration error goes down, so again you'll have a trade-off. However, they mentioned that most state-of-the-art networks, because they use batch normalization, they usually stay around here, so this is not much of an issue, actually. Now we can go to the third part of the paper.
Just a question.
Yes.
Can you elaborate maybe a little bit behind the intuition behind the fact that the more parameters, the more ill-calibrated you become, because it's not very...
Yeah, they actually describe it with more detail in the paper, and it has to do with the fact that if you are mostly correct, let's go back to the formula that is actually important here, which is the can I write down in any of these words?
Yeah. It's not my stuff. But
That's fine. Okay, sorry.
There's nothing on the other side. You want to use the other one?
Yes, or the other side.
Do I release this and sort of flip upside down?
Well,
Just flip it, top to bottom. That. Okay, it's meant to make that sound.
that's good. So what is, I'm not taking the view of it. So if you were to plot these formula, you get something like this. So this is the probability for a certain class, the output probability for a certain class. It is, and this is the loss. And the plot is shaped like this. Now it's more, well, depends on the scale, but so this is 1, this is 0. It's more like
Probability of what?
it's the loss landscape of the cross entropy. So what you get here is that, oh, this is for the correct class, by the way. So if
So training starts up here and ends down there.
yeah, exactly. So if if your network wants to, if the ground truth is a certain class and your network says that it has a probability of 0, the loss will be super high. But if it says it has a probability of 1, the loss will be 0. And the goal of the training is to get as close to 0 as possible. This is the thing you are trying to optimize. Minimize the value of this function. So if most of your predictions are correct, most of them will be around here, correct? And for every incorrect one, they will probably be, well, somewhere around here, but the main take is, because most of your network is around here, they are mostly correct. There are so few samples that are in this area that the network has more to gain in terms of this metric to push everything in this direction than to actually produce a calibrated output.
So, you're saying calibrated output is an accident on the trained networks?
Sorry?
That you ever get calibrated output out of the neural network is an accident?
Yes.
Okay.
Well, not an accident. I mean, the network actually tries, well, we can say it's an accident, but for me it makes a lot of sense that the network learns the correct things. Maybe there is like an actual explanation, but I don't know exactly.
So is it because training is, your goal of training is not getting calibrated outputs,
It's
but
to
getting
minimize
accuracy.
this. Yes.
Right. So
Yes.
whatever calibration you get is just an artifact, right?
Yeah.
Because you're not trying to actually achieve that.
Yes, that's not your
So
goal.
I think that one of the things that they argue in the paper as well is that most modern networks are optimized for accuracy, or F1 score or something similar, which is interesting if the machine learning algorithm is a standalone system, right? If you want to classify images or classify text, the machine learning algorithm is its own AI system, so it's alone. But when you introduce that into a bigger system, then you not only want to be, you not only want to have accuracy, but you also want to be accurate when you're wrong. So if you see the reliability diagrams, when it says, so when you have a small output, you want to make sure that that small output is also correct, and that means the network recognizing that, well, if it's 0.2 output, then 20% of the time is all that you're going to get right for this particular class. But that loss function does not optimize that. It just tries to make everything as high activation as possible. And well, what the other plots showed is that all the other techniques that have been added in recent years on top, so making them deeper, wider, adding batch normalization, and using less weight decay, it all makes for better accuracy, but it makes for worse calibration, because the networks don't need to be calibrated because they're mostly right most of the time, right?
So if a simple answer to my question is, we don't get good calibration because it's not an objective, in effect.
Indeed,
Yes.
it's not the objective
Yes.
of
So
the training.
we interpret the softmax as a probability, but it's not built that way.
Yeah, indeed. I think one of the problems is that we lost sight of what calibration was. We took it for granted because it was, in the early networks, they were properly calibrated, and then everyone said, okay, let's just focus on accuracy, and we sort of lost track of calibration.
Just to wrap up this question, if you think about it, if you have a probability of 0.8 and this is the perfectly calibrated network,